Well, thank you very much for the invite. I was really hoping I would get to go to Buenos Aires, but uh, this is nice too. It's nice seeing you all. So originally I was going to talk more about computing the third Gerstenhaber-Schack bialgebra cohomology, but I will stick with sort of older stuff, which is about the computing the second one. And I apologize to the people who have already seen large parts of this talk. So before I even tell you how we compute this cohomology theory and what it is, let me motivate it a little bit. So we start with Hopf algebra with the Chevalier property. What do I mean by that? It's that if we look at the co-radical, that's the sum of all simple subcoalgebras. Which is in general just a subcoalgebra, but it should be a Hopf subalgebra. Yeah? So this co-radical, of course, is a notion completely dual to the notion of a radical for algebras. And just like you have radical filtration given by the powers of the Jacobson radical, here you have the co-radical filtration. And of course, in general, this is just a coalgebra filtration, but if the zeroth piece is also a subalgebra, then this is a Hopf algebra filtration. So throughout the talk, I talk about Hopf algebras, but really, I will not talk about antipode at all. It won't appear in formulas, but it is important that these bialgebras I'm dealing with are Hopf algebras because certain things that I'll talk about otherwise are not true. So we look at this Hopf algebra filtration, and then we can look at the associated graded, and it's not completely trivial, but not that hard either. This carries a natural structure of a Hopf algebra again. And now including the zeroth piece and then projecting onto zeroth piece, this gives us a configuration of what is called, what Radford called Hopf algebra with a projection. And if we look at the coinvariance under this projection to the zeroth piece, that is a graded connected Hopf algebra, well, not in vector spaces, but in the category of Jeter-Drinfeld modules over H, the co-radical of this initial U that we started with. And this B then decomposes as by connected in this graded setting. Of course, I just mean that zeroth piece is one dimensional. And B decomposes as to what is now usually called Majid-Radford bosonization, or a Radford byproduct of this A and H. This kind of idea, of course, was resurrected in the 90s by Andrushkevich and Schneider when they were classifying certain kinds of pointed Hopf algebras. But actually, the original idea goes way back into the 50s, where people were describing what co-commutative Hopf algebras look like. And of course, in that setting, we don't need to go into this category of Jeter-Drinfeld modules, because in that setting, if this B was co-commutative, of course, then the coaction of H on A is trivial, and so this bi-smash product is just a smash product, more or less direct generalization of what a semi-direct product would be in group theory. And well, this A, there's a lot of machinery of describing this A, which I will not mention today. But so if A is generated by its degree 1 elements, then this A is what's called a Nichols algebra, right? Which can be described in combinatorial terms using arithmetic root systems and such. But it's a beautiful theory, but one would need several talks to talk about this, and I'm not exactly an expert anyway. Okay, so next is sort of the lifting problem is how one would, starting with this B, some co-radically graded Hopf algebra. Well, it doesn't even need to be a co-radically graded Hopf algebra, just any graded Hopf algebra. And again, by graded, I mean graded by non-negative integers. How would one describe all filtered structures on it, all liftings? Yeah, by liftings, I mean filtered Hopf algebra structures U on B, so, whose graded recovers the B. Yeah, and I give you a deformation theoretic approach to this. So if you start with any filtered structure on this same underlying vector space, graded vector space B, it can be identified with a graded structure on the polynomials in one variable with coefficients from B, where you proclaim this indeterminate T to have degree 1. In other words, this is sort of just a dummy variable that you could think of it as a dummy variable that makes all these maps, these filtered maps, mu and delta u now graded, right? Because B, remember, was a graded vector space, so all these filtered maps will decompose into locally finite sums of homogeneous maps of various negative degrees. Only the maps in negative degrees show up, yeah. And now you just stick in the T, and now in this our polynomials, they become graded maps. Yeah. So why would you do this? Well, because there is a rich and very nice theory of graded deformations that goes all the way to Gerstenhaber, right? So in general, if you start with any naturally graded vector space with some structure, be it algebra, Lie algebra, bialgebra, and so on, then its formal graded deformations will be polynomially linear structure on polynomials of T over T with the degree of T being 1. So of course, in the ungraded setting, formal deformations always land in the power series, right? And a priori you could try this here, but because of this local finiteness, everything you're interested in is already encoded in polynomials. So there's no reason to go to power series, even if a priori you wanted to. That will not give you any extra thing, right? So that's why we are just dealing with polynomials. So in this setting, the graded deformations are much nicer behaved than general formal deformations. Yeah. And deformations of graded rings and their relationship to filtered rings was already discussed in this original Gerstenhaber paper. Yeah. And then in the 90s, Braverman and Gatesbury wrote this beautiful paper on deformations of quadratic algebras, and then for bialgebras and the connection of this with the Andruszkiewicz-Schneider lifting method was first studied in early 2000s by Du Chen and Yi. Okay, so what is the cohomology? So normally when you do this, of course, the point is the infinitesimal deformations will be described by second cohomology group, and obstructions to integrating or continuing partial infinitesimal deformations will be described by the third cohomology group, right? And that's exactly what happens here. So what is the cohomology considered here? So this is the total cohomology of a double complex where the PQ node is just linear maps from the pth tensor power of B to the qth tensor power of B. But here it's very important, right, that it's truncated, right? You start at P and Q being 1. Yeah. So not to be confused with the usual untruncated Gerstenhaber-Schack bialgebra cohomology, which turns out, I mean, you can prove with not that much work that that one is just isomorphic to the Hochschild cohomology of the Drinfeld double of B with trivial coefficients. Yeah. Meaning coefficients, the ground field, where B acts on the ground field via the co-unit. Yeah. So the horizontal differentials are just what you need for computing Hochschild cohomology. Of course, the action of B on the qth tensor power of B is just the diagonal action, and in vertically you do the dual of this. It's usually referred to as the Cartier differentials, Cartier cohomology, and the coaction of B on the pth tensor power of B are given again diagonally. Yeah. And the cohomology, that there is a convention you shift when you take the total cohomology of this. The convention is you shift it by 1, and well, I mean, one reason is that one of the reasons is that it makes it convenient, so that in this way the second cohomology will again be the one precisely responsible for infinitesimal deformations, and H3 will be responsible for obstructions. Yeah? And the point is, when B is graded, then for any integer L, doesn't have to be a natural number. For any integer L, you can consider homogeneous maps of that fixed degree, and actually for these formal graded deformations, only negative L's are of interest. Yeah. So this is, explicitly written in terms of maps, what, the second cohomology will look like. So you will recognize some of these conditions, right? So second cohomology is pairs of maps F and G, where F is essentially, I'm writing it on as defined on the augmentation ideal or positive part, just so to avoid writing the unit and co-unit conditions being normal and co-normal. Yeah. So this F will be exactly a Hochschild co-cycle. Yeah, and it has to be because it will be responsible for associativity in the deformation. This G will be the dual of that, the Cartier co-cycle, which will be responsible for co-associativity of the deformation, right? And then F and G have to be compatible in this sense, and this was precisely responsible for the compatibility of multiplication and co-multiplication in the deformed structure. And the two co-boundaries are pairs of maps, which where F is a co-boundary with respect to some H, and G is, well, because of this sign trick, negative co-boundary, but of the same H. That's the point. Yeah. Okay, so how does this relate to infinitesimal deformations and obstructions, right? So, well, if you start with any formal graded deformation and say that mi delta I are 0 for a while, and then you look at the first non-zero 1, well, then this first non-zero 1 is precisely a 2 co-cycle in degree negative R. And if you have found sort of a partial deformation, deformation mod t to the r plus 1, then you can try to extend it to a partial deformation 1 degree further. And the way you could theoretically try this, I mean, in practice, this is almost impossible, but the way you could theoretically try this, you can compute some funny expression. I don't mean that this is some sort of Lie bracket or anything. This is just ad hoc notation. You use some funny expression in terms of the first R of them, and that funny expression will always be a 3 co-cycle. And if it is actually a 3 co-boundary, then you can go one step further. In this graded setting, it's very nice, right? In ungraded setting, then it's not so clear, but in graded setting, it's very nice, because if you can continue somehow, then the second cohomology, now in 1 degree lower, a homogeneous degree lower, will again tell you all possible ways of continuing. Yeah. And vice versa, right? And of course, the equivalence class of this partial extension only depends on the cohomology class of this, right? So that's where co-boundaries come in. All right, so now I'll discuss some phenomena that's really very particular to this quantum world, and it's I found it amazing that it occurs, right? So I'll define something called cohomological homogeneity of some class of liftings or formal deformations. So if you take any pair of deformations or liftings, then you could define their infinitesimal difference to be just the difference in the first piece where they differ. Yeah. And it turns out, and it's not hard to prove, that up to equivalence, the infinitesimal difference between two non-equivalent extensions will always represent a non-zero cohomology class. And let's call this the infinitesimal cohomological difference. And now I'll call a set of deformation deformations cohomologically homogeneous if at every point every possible cohomological difference can be identified. Yeah, so, and of course in classical situation, I mean, this would it would be ridiculous to expect that something like this would exist, but in this quantum world it seems that in many examples it does. Yeah. Now it's of course obvious that any cohomologically homogeneous set of deformations must contain all deformations up to equivalence, but why the converse would be true ever is a bit mysterious to me, but I'll talk a little bit about this. Yeah. Now, of course, if the theory is completely unobstructed, then the lifting problem will be cohomologically homogeneous, and I still have no reason to believe that converse would be true, although I'm suspecting that maybe in some sufficiently quantum situation it does. I'll mention this again. So let me give you now first a non-example, a classical example where of course the lifting problem will not at all be cohomologically homogeneous. So again, this was mentioned already today. Thank you very much, Susan, for talking about symmetric algebras. So if I take a symmetric algebra over some vector space, yeah, then it's easy to see by hand that the second cohomology group in degree -1 is in bijective correspondent with antisymmetric maps from V tensor V to V. Even more precisely, every cocycle it will be cohomologous to a cocycle of the form f comma 0, where f will be uniquely determined by its values on V tensor V. And a cohomology class of this f will only depend on antisymmetrization of f. So might as well assume that you started with an antisymmetric one to begin with. So its antisymmetrization will then just be 2f. Yeah. And of course, most of them are very much obstructed. It turns out, that they are unobstructed. They can lift even 2 degrees further, if and only if you get the Jacobi identity. Yeah. And then, of course, the liftings will be precisely the universal envelopes of Lie algebra structures on V. So here you see, like almost every or a lot of infinitesimal ones will not at all lift to a formal deformation. Yeah. So the lifting problem here is not at all cohomologically homogeneous. And let me briefly mention, give you the simplest sort of non-trivial example. So this so-called Radford Hopf algebra. This is a slightly enlarged Taft algebra. If Taft algebra would, everything would be trivial. So this is sort of the simplest non-trivial example. So as an algebra is generated by 2 elements, G and X, where G is of order m times n, and X is nilpotent of index n, and coalgebra structure is given by G being group-like and X being skew primitive. Yeah, and now you can explicitly define a map from B tensor B to the ground field, and then you can make it into a map from B tensor B into B by this formula. Here I'm just using the abbreviated Sweedler-Heinemann notation for coproduct. And then you can see that the second cohomology in degree -n is precisely one-dimensional, spanned by this f comma 0, and it's 0 in all other negative degrees. And in this case, actually, this is one of the cases where we can actually compute H3, or compute is a hard word, prove that it is trivial. Yeah. And then so automatically the lifting problem must be cohomologically homogeneous, and these are all the liftings. Yeah. So okay, so how about some ideas of how to how to compute, say, this H2? Yeah. Well, because of the truncating of this double complex before you take the total, right? You get a short exact sequence of double complexes, which leads to a long exact sequence in cohomologies, yeah. And so you get this connecting homomorphism between the Hochschild cohomology of B with trivial coefficients, where K is considered a B module via the co-unit, and this truncating Gerstenhaber-Schack cohomology. And actually, you can explicitly write down what this does, right? If you have a cohomology class generated by Simon cycle F, then you get F comma 0, where this is given by this same formula, which you might recognize from the previous slide. Yeah, and then with Sarah, this was roughly some 15 years ago. We have proven that for negative L and B from this Andrushkevich-Schneider classification program, meaning B is finite dimensional and the co-radical is a group algebra of an abelian group not having small prime divisors, then this homomorphism, which of course is trivial in the classical case, of symmetric algebra. This homomorphism is the zero. I mean, this map is the zero map, so it really is not useful. But in this quantum setting, it is homogeneous, and actually you can also prove that lifting problem is cohomologically homogeneous. Yeah. And then a few years ago, when I was in Argentina and I was learning a lot of nice things from Gaston, we revisited this, and we generalized this result quite a bit. So if we define M of A to be the kernel of the multiplication map on this the set of these coinvariants, then the algebraic dual of this M of A can be identified with the H-stable part of cohomology, which of course is just equality if H is semi-simple, right? And then we have proven in also joint work with Fernando Fentino that if H is co-semi-simple and unimodular and L is negative, and B doesn't even have to be generated as an algebra in degree 1, but only in small degrees, then and this is sort of a mysterious condition, but it seems to be satisfied in every explicitly described case I have looked at so far. There are no Jeter-Drinfeld maps from this M of A to the primitives of A, primitives in the the category as Hopf algebra in the category of Jeter-Drinfeld modules. Then this map that I talked about above will always be surjective. And this M of A is really not that mysterious, because if A is say a Nichols algebra, which you write as a tensor algebra, free algebra on V modulo some ideals, this M of A is really just ideal modulo its positive part. Yeah, and so if there are no Jeter-Drinfeld maps from ideal modulo its positive part into V, then this map will be surjective. And in particular, if you can find a nice set of relations, and I mean, and R is sort of the Jeter-Drinfeld module generated by the relations, and there are no Jeter-Drinfeld modules from R to V. So remember, I mean, most of the time we are dealing with the semi-simple case. This just means that no simple summand of R is the same as any simple summand of V, right? That's all this says. Yeah. Then the algebraic dual of R, then you get this surjective homomorphism from the algebraic dual of R into this cohomology that is responsible for formal deformations. Yeah. So here is an example of the work we did. This is sort of more like a proof of concept, because before that, this was just sort of used to explain liftings looking the way they do after the fact. But this is, I think, the first project where we use this theory to just compute the liftings in a case where they did not liftings were not known, right? So if you take H to be a dual of a group algebra of a dihedral group, where well, the order of this dihedral or is divisible by 4. So then we can, of course, already use the explicit description of all Nichols finite dimensional Nichols algebras that was previously given by Fernando and Gaston, and we can, by what I just discussed on the previous slide, compute explicitly all the infinitesimal deformations, and we can also see that all of those lift. We don't compute H3, but we use sort of formal deformation formulas by showing that actually each infinitesimal one described to a multiplicative cocycle twist. I call it twist here. Gaston was calling them in his talk cocycle, two cocycle deformations, yeah, via an exponential map. So the lifting problem is always cohomologically homogeneous, and we can actually describe then all possible liftings this way. No, I'm out of time. I'll just briefly mention a couple more things for a minute. So, you know, I already discussed that in the trivial braiding, Lie structures on V correspond precisely to graded bialgebra deformations of the symmetric algebra. And of course, the exact analog of the symmetric algebra is the Nichols algebra, yeah? And this is actually true for any symmetric braiding. And so one could think of formal graded deformations of the Nichols algebra as somehow virtual Lie structures on V. And so the question that I occasionally work on, and with not much success yet, is can we find some nice examples of deformations of Nichols algebras with non-symmetric braiding? Well, the one place where you cannot look is finite dimensional Nichols algebra, so because those are actually rigid, yeah? So, well, we don't know if all of them are rigid, but if in the previous work with Ivan Anchiona and Misha Kochetov, we have shown that if the braiding is symmetric, coming from a finite dimensional cotriangular Hopf algebra, then this will always happen. And it will always happen that they'll be rigid if the braiding is diagonal. And sort of the idea of the proof is that the core is exactly the same condition, cohomological condition, as I discussed before. And so let me leave you with some questions, right? So if I start with, so bi-smash product or Radford byte product of A and H, where A is some nice quotient of the tensor algebra. So the question would be, there's sort of the same reason for both, but is there maybe a more direct link between rigidity of A as graded Hopf algebra in the category of Vieter-Rimfeld modulus and surjectivity of that map? Connecting homomorphism I talked about, or is any of this sufficient for the set of all liftings to be cohomologically homogeneous, or why would they all have to be cocycle twists of each other? And last but not least, and this is what I've been thinking about quite a bit, suppose we have this Nichols algebra, does it always follow that there are no Vieter-Rimfeld maps from the positive part of I to V? So is finite dimensional enough, or maybe more generally, finite Gelfand-Kirillov dimension where the braiding is sufficiently quantum, whatever that means. Okay, I will stop here. Thank you very much for your attention.